Everyone, if you are a parent, I want you to begin with a question. Have you ever seen your child successfully complete 20 math questions at home and then struggle when the examination asks the same question in a slightly unfamiliar way? And if you're a student, perhaps you've experienced this yourself. You look at the solution afterwards and think, I knew this. That sentence, I knew this, tells us something extremely important about Cambridge O level math exams, right? Knowing mathematics is only part of the challenge. The other part is recognizing when to use it, how to connect, how to connect different ideas, and how to communicate the reasoning clearly enough to earn the marks, okay? That is what I mean by engineering the mathematical mind. Today, I don't want to, I don't simply want you to show you a list of topics. You can find a list of topics anywhere. Just Google it, right? I want parents and students to understand the architecture of Cambridge O-level mathematics syllabus D 4024 for the years 2025 to 2027 examination cycle. So if you're taking the exam next year, and you know, uh, this is for you. So what is Cambridge actually expecting? Why do some students who appear good at maths still struggle? And why has non-calculator fluency become so important? What is the difference between knowing a technique and solving an unfamiliar problem? And most importantly, how should a student prepare, right? The current syllabus contains 9 major subject areas and 2 examination papers. But underneath those topics is a much more important idea. Right? Cambridge is trying to develop a student who can think mathematically, not merely imitate a worked example. That is the journey I want to explain today. Okay? So look at the 5 words on the slide: confident, responsible, reflective, innovative, engaged. Parents notice that none of those words are fast calculator, right? And none is memorizes formulas. That is significant. Mathematics is certainly about techniques. Students must know how to factorize. They must know how to work with fractions, right? They must understand trigonometry, probability, stats, and geometry. But long-term objectives is larger. A confident learner can look at a mathematical problem and begin. They do not, immediately see, I've never seen this exact question before. A responsible learner understands that mathematics requires ownership. You cannot learn mathematics simply by watching someone else solve problems, right? You can do that all day, but you still don't learn. At some point, you have to pick up the pen and struggle with a question. A reflective learner checks an answer. Does it make sense? Should this length really be negative? Should this probability really be greater than 1? Have I rounded too early? And an innovative learner can take familiar tools and use them in an unfamiliar situation. And an engaged learner begins to see mathematics not as hundreds of disconnected rules, but a system of patterns and relationships. Students, this is important for you, okay? When you get a difficult question wrong, the question is not simply, which formula did I forget, right? Sometimes the better question is, what connection did I fail to see? That change in thinking is extremely powerful. All right, so what successful mathematics learning develops, right? I like to simplify the development of a strong math student into 3 areas. The first is attitude and resilience. The second is fluency and logic. The third is communication and application. Let's just start with resilience. Okay, there is a moment in math when almost every student feels uncomfortable. You read the question, you don't immediately know what to do, right? That moment is not evidence that you're bad at math, right? That moment is often where real mathematical thinking begins. Look, weak preparation teaches the students if I don't immediately recognize the question, I can't solve it. And strong preparation teaches, let me identify what I know. Let me draw something. Let me write an equation. Let me look for a relationship. That is resilience, my friends. Then comes fluency. Fluency means that basic mathematical operation should not consume all of your mental energy. If simplifying a fraction, manipulating a negative number, or rearranging an equation requires enormous effort, it becomes very difficult to solve the larger problem built on top of it, right? And finally, communication. This is where many students underestimate Cambridge math. The answer alone is not always enough. The student has to demonstrate a valid mathematical method. The working must tell a story. Right? What did you know? Or what did you calculate? What did the rest, what did the next step follow, right? And parents, listen, when you talk about developing a strong mathematics subject, these three areas have to grow together. Confidence without technique is not enough. And technique without reasoning is not enough. And reasoning that cannot be communicated may still lose marks. Okay? So, the five pillars of mathematical architecture. Officially, Cambridge organizes its syllabus into 9 topic areas. For teaching purposes, however, I find it helpful to connect them into 5 larger pillars. Think of this as a building, right? The first part is a number. This is the language. The second is algebra and graph. This is the logic. Then we have geometry and coordinate geometry. This gives mathematics physical structure. And next comes mensuration and trigonometry. Now we can measure that structure. And finally, we have, statistics, probability, transformations, and vectors. These allow us to reason about data, uncertainty, movement, and direction. Now, here's the key idea. Students often study mathematics like this. Chapter 1, finish it. Chapter 2, finish it. Forget it. That's dangerous because the examination does not promise to keep ideas in separate boxes, right? A geometry question can require algebra. A trigonometry question can require Pythagoras. A graph question can require functions. A probability question may require accurate manipulation of fractions. So instead of thinking, I completed the chapter on algebra, I want you asking, can I recognize algebra when it appears inside another problem? That is a much higher standard, and it is much closer to the standard demanded by the examination. Okay? So let's look at pillar number 1, right? Parents, sometimes, you assume this must be easy part because the students have been working with numbers since primary school. But look at what number becomes at this level. Prime factors, HCF and LCM, fractions, decimal, percentages, indices, right? Standard form, surds, bounds, rates, exponential growth and decay. These are not isolated tricks. They are the vocabulary that support almost everything else right? Take percentages. As at a basic level, find 10% of 500, very straightforward, right? But now put percentage into repeated depreciation. A car loses a percentage of its value every year. Now the student has to recognize that this is repeated multiplicative change that leads naturally to exponential growth and decay. Or consider surds. The student may produce an exact answer, such as the square root of 20. But can the student simplify it? Can they rationalize it? Can they preserve an exact value rather than immediately reaching for a decimal? This matters particularly because paper 1 is a non-calculator examination, okay? The 2025 syllabus revision placed explicit emphasis on topics including exponential growth and decay and surge. So parents should be cautious about assuming that older notes or an older teaching sequence automatically reflects the current course. Number is not merely arithmetic. It's precision, right? And precision is one of the functions of success in every other pillar. So pillar two, uh, algebra and graphs, right? And this is where we begin moving from calculation toward abstraction. A number gives you a value. An algebraic expression gives you a relationship. That is a major intellectual step. Students need to expand and factorize expressions. They need equations and inequalities. They need simultaneous equations, quadratic equations, sequences, functions, inverse functions, composite functions. And then they need to see those relationships graphically. So let me give students a simple way of thinking about this. An equation is not simply something that you solve. It is a statement about a relationship. A graph is a picture of that relationship, right? Once the students understand this, algebra and graphs stop feeling like unrelated chapters. They become two languages describing the same idea. And notice the practical graphs on the slide, right? Distance time graphs, speed time graphs, acceleration and deceleration. The area underneath a speed time graph can represent distance traveled. The gradient can tell us something about rate of change. So suddenly, algebra and graphs are connected with movement in the real world. Okay? This is exactly the kind of transition that students must learn to make, from symbols to graphs to interpretation. The stronger student does not merely know how to manipulate algebra. The stronger student understands what the algebra is telling them. The distinction becomes increasingly important as questions become, less routine. Now, the third pillar, geometry and coordinate geometry, right? Geometry is, sometimes taught as a giant collection of facts. Angles on parallel lines, properties on triangles, right? Properties of polygons, circle theorems, bearings, constructions, and students try to memorize everything. But strong geometry is really about reasoning from structure. Suppose I give you a circle and tell you that a line is a tangent. That word tangent gives you information. Suppose I tell you two lines are parallel. That information gives that gives you information. Suppose I tell you two shapes are similar. Again, that gives you information. The successful student learns and turn mathematical vocabulary into consequences. Okay. So coordinate geometry then connects the visual world back to algebra. We have coordinates, gradients, midpoints, lengths, parallel lines, perpendicular lines, and equations of straight lines. Numbers supports algebra, and algebra supports graphs. Graphs connect with coordinate geometry, right? So geometry connects visual reasoning and algebraic reasoning. The subject, is beginning to join together. This is also why simply memorizing one worked example is fragile. Right? Change the diagram and the student becomes lost, right? But teach the underlying relationship that the student can reconstruct the solution. And that's what we do. And parents, that is one of the main differences between short-term examination drill and genuine mathematical preparations. Okay. So now let's go to mensuration and trigonometry. Imagine we want to measure the physical world, right? Lengths, areas, volumes, angles, heights, distances, 2 dimensions, 3 dimensions, that bring us mensuration and trigonometry. Students must work with areas and perimeters, circles and sectors, surface area and volume, compound solids, and solids such as cylinders, cones, spheres, pyramids, and frustums. Then trigonometry gives us a new set of tools. Pythagoras, sine, cosine, tangent, sine rule, cosine rule, right? The area formula for a triangle, and eventually three-dimensional problems. Here's where students often make a revealing mistake, right? They ask, sir, is this sine question or a cosine question? But the exam is not obligated to tell you that. The real skill is determining what information do I have. What am I trying to find? Which relationship connects those quantities? That is the mathematical decision making. Three-dimensional trigonometry makes this even more important, right? You must first find a hidden length in one plane before using it in another triangle, right? Now we are no longer performing one procedure. We are building a chain of reasoning. And that is exactly where practice must progress from routine questions toward multi-step problems. So the pillar five is stats, probability, and vectors, right? They help us navigate information, uncertainty, movement, and direction. Statistics ask, what does the data tell us? Students work with average and measures of spread, scatter diagrams, correlation, lines of best fit, cumulative frequency, histograms, and frequency density. And one of the most important stat skills is not simply calculating it, it is interpreting it, right? What conclusion can I reasonably draw from this data? And just as importantly, what conclusion can I not draw? Right? Probability then asks us to reason about uncertainty, single events, combined events, sample spaces, Venn diagrams, tree diagrams, even with replacement and without replacement, right? Again, the mathematics becomes a model of real situation. Finally, vectors and transformations deal with direction, magnitude, and movement. Reflection, rotation, enlargement, translation, vector addition, scalar multiplication, vector geometry. Students sometimes see these as separate chapters, but notice what is happening across the entire course. We're teaching the student to represent reality mathematically, right? A graph represents a relationship. A diagram represents space. A probability tree represents uncertainty, right? A vector represents movement. That is why representation is such an important mathematical skill. So now let's talk about the mathematical ecosystem, okay? This may actually be the most important slide in the presentation because this is where the pieces come together. Number gives us language, algebra gives us the logic, geometry give us the structure and measurement, stats and probability help us navigate information and uncertainty. These are not separate islands, they are an ecosystem. Let me give you a simple example, okay? Imagine a question involving the design of a circular water tank. You need geometry to understand the shape, mensuration to calculate volume, right? Algebra to rearrange a formula, percentages to calculate an increase in capacity, and perhaps a graph to compare different designs. So 5 different areas could appear inside what looks like one question. This explains a very common experience, right? A student says, I understand every chapter when my teacher teaches it. Excellent. But can the student determine which chapter is relevant when the examination does not label the question? That is the next level. That's where you need to be. Okay? So our preparation has to change over time, right? At the beginning, yes, isolate the skill, learn it carefully, practice it, build fluency. But then start mixing topics, start moving the labels, start introducing unfamiliar words. Okay? Start asking the student to choose the strategy. That is how we move from chapter knowledge toward examination readiness. Okay? So here's the assessment strategy, right? Now, parents, look, this slide is particularly important because we need to understand how the student is actually assessed, right? There are 2 papers. Paper 1, non-calculator, 2 hours, 100 marks. 50% of the qualification, right? Paper 2, calculator, also 2 hours, also 100 marks, also 50%. Now, I want to correct a common misunderstanding. Part 1 is not simply the easy technique paper, right? Well, paper 2 is the thinking paper. It's not that. Both papers contain structured and unstructured questions. And both papers assess knowledge and technique as well as analysis, interpretation, and mathematical communication. The major difference is the tool, is the tool environment. On part one, the student cannot rely on a calculator. That means fraction matter, mental arithmetic matters, right? Exact values matter, number sense matter, algebraic manipulation matters, right? If a student has become completely calculator dependent, paper one will expose that weakness very quickly. Paper two requires a scientific calculator, but the calculator is a tool, not a substitute for thinking. Right? The student still needs to set up the problem correctly. It still needs to know which operation to perform. It still needs to interpret the answer. It still needs to show necessary working, right? And students should also know that graphical and algebraic calculators are not permitted, right? So the current preparation strategy is not let's prepare separately for the easy paper and the hard paper, right? It is let's develop the mathematics deeply enough that the student can operate with or without the calculator. Right? That is a much more accurate way to prepare. So what are the assessment objectives, right? We arrive at what I want every parent and student to understand. Cambridge drives the assessment into two broad objectives. AO1 is knowledge and understanding of mathematical techniques, approximately 40 to 50%. And AO2 is analyzing, interpreting, and communicating mathematically, approximately 50 to 60%. Think of what that means. If a student spends almost all of their preparation doing routine questions where the method is obvious, they're preparing for only part of the challenge. AO1 matters enormously. Okay, it is the foundation. Can you recall technique? Can you perform calculation? Can you use the correct notation? Can you work accurately? But then comes paper two, right? Can you identify a strategy? Can you interpret information? Can you connect several steps? Can you make a logical inference? Can you communicate your mathematical method? This is why the student who says, but I knew all the formulas, can still be disappointed with the result. The examination is not merely asking, what do you know? It is asking, what can you do with what you know? All right. What can you do with what you know? So our practice should have levels, right? First, learn the technique, then apply it, then use it in unfamiliar and multi-step situations, and finally explain and verify the reasoning. Students, you get a difficult question wrong, do not simply look at the answer and say, oh, I understand. Ask yourself, at what stage did I fail? Did I not know the technique? Did I fail to recognize which technique was required? Did I make an algebraic error? Did I misunderstand the diagram? Did I round incorrectly, right? Did I fail to communicate enough working, right? That is how mistakes become useful. So from assessment skills, so mathematical habits, right? And let's return to where we started. Confident, responsible, reflective, innovative, engaged. The exam itself is formally assesses, right, mathematical knowledge, analysis, interpretation, and communication. But when students are taught properly, the process of preparing for those demands can develop those wider habits. A confident student does not panic when the question looks different. A responsible student practices independently instead of relying entirely on the teacher. A reflective student checks their method and learns from errors. An innovative student adapts familiar tools to unfamiliar problems. And an engaged student begins seeing connections. That, in my view, is what makes mathematics education valuable beyond one examination, right? Of course, we want the grade. Grades matter. But we also want the student who finishes this course to think differently from the student who started it. Parents, if you remember only one message from this presentation, let it be this. Do not measure mathematics preparation only by how many chapters your child has completed. उनसे मुश्किल सवाल पूछें. उनसे ये पूछें कि can you solve without being told the method, right? क्या आप अपना काम जो आपने किया है जो जवाब है वो एक्सप्लेन कर सकते हैं? Can they connect two topics? Can they handle an unfamiliar problem? Can they work accurately with a calculator, right? And can they identify and correct their own mistakes? क्या वो जाकर के अपना काम फिर से चेक करते हैं? क्या वो उनको समझ में आता है कि यार हमने ये प्रॉब्लम की थी, अब हमें ठीक करना है, right? Those are much stronger indicators of readiness. And students, listen to this, right? You do not become strong at mathematics by avoiding difficult questions. You become strong by learning how to stay with a difficult question long enough to make progress. That's the key word, long enough, okay? आपको अगर शुरू शुरू में समझ नहीं आ रहा, आप मिस्टेक करते जाओ, लेकिन उसको करते जाओ, सोचते रहो उसके बारे में until के वो it sinks in. The objective is not to memorize hundreds of solutions, right? It is to develop a mind capable of building a solution. Okay? That's what I mean by engineering the mathematical mind. And that is the standard we should be aiming for in Cambridge O level. Okay? Thank you very much. If you want to learn more about the courses that we teach, or if you want to register, please click on the link and fill out the form and give it a try. Maybe I'm able to help your student. You'll find out very quickly. I promise. Thank you.